Today, we're going to talk about finite element analysis, but rather than get into using the software, I'm going to walk you through some of the mathematical basis behind the finite element analysis. I know that's not what you want to do, but really, in order to be a more competent engineer and be able to use the tool really effectively, you need to have at least an introduction understanding to what's behind it all. Now, keep in mind that when I talk about going through the background math, that I'm really going to be spending in the next 20 minutes or whatever it takes, the sort of discussion that really glosses over the really interesting, difficult bits. The sort of mathematics we're going to be doing relies on your background in calculus. And really, there's a whole semester's worth of lectures on the basis of finite element analysis. It relies on a lot of stuff, and I'm not going to be covering it in detail, certainly not enough for you to be competent in understanding the detailed math. I hope, however, it will be enough to make you functional in using the tools. So we're going to talk about a simple example, and in this case, it's just simply a bar of some material that has a temperature on one end that's constant, a heat flux on the other end that's constant, and insulated top and bottom. This is a steady state problem, so nothing changes in time, and everything that we have here should be well seen in some of your math courses. Now, you know from heat transfer that the solution for this should be essentially a linear temperature gradient from the warm side, T0, to the outside, kind of like the temperature through the wall of your house through insulation. That's the simple problem we're looking at. Now, we want to write down the differential equation for this, and this is also pretty standard. You'll find it in most of your math textbooks. It's d squared t dx squared, and you can derive it by a simple differential element as shown here. I'm not really going to get into the derivation too much, but if you've seen that differential equation before, it should be familiar to you. Key thing about this, it's a boundary value problem where you've got boundary conditions at opposite ends. The temperature boundary condition is called an essential boundary condition, and the other is a natural boundary condition where you know the heat flow. So there's that differential equation, and we could discretize that. We could make it into discrete elements, and that would mean we'd be looking at the temperature over individual points on a distance line. And if we could discretize that, the first step would be in discretizing the first derivative of this temperature function, meaning that we define it, let's say, at one point ti, and then we say the slope of ti is compared with ti I minus 1. Now, we have a problem because what if we use the opposite side? Which one's right? Do you use ti plus 1 to ti or ti to ti minus 1? Well, this is the finite difference method, and it's picking which of those makes it a finite difference solution. And those two solutions are called the upwind difference or the downwind difference method. There's also a central difference method. The way that you choose that really defines how your problem evolves. If you pick a dt dx in one way, it comes out as one form, and you end up with a constant at each of those derivatives. And it might be different constant depending on whether you use an upwind or a downwind scheme. Now the key is right there at the intersection where the points were, it's undefined. So if you try to do the second derivative of a stepwise function like that, you have a problem. And while we could still write the equations for the discrete second derivative, it's going to end up being a long, nasty thing. And in fact, if we write it out, it involves a whole bunch of terms on either side of the point I. In fact, 5 points as a minimum to give you the second derivative. So if you get close to the boundaries, then you've got a problem. So, finite difference. The key is that there are no assumptions of what the solution looks like, that the delta x, or the spacing of the grid, is fixed, that means it's a regular grid. It's very rigid. And that can be a problem in some conditions. You have to decide between an upwind, downwind, or center difference scheme. Each one gives you a slightly different result and is appropriate for slightly different conditions. Ultimately, it's a discrete differential equation. Now we could take another approach. Rather than discretizing the differential equation, we could look at the discrete solution directly. And we could say, we're going to assume that we've got points t0 through t1 that have discrete solutions, and we're going to pick an arbitrary weighting function, we, which also has discrete values and discrete points. If we multiply those two things together, in the case of our existing differential equation, and this is only an example, multiply we, which is an arbitrary function, by d squared t dx squared, and that multiplier still needs to be 0. We could then integrate it, and if the equation itself was 0, the integral will still be 0. Now, the key is that if it's going to be any arbitrary function we, the only way that could be true for arbitrary we is if d squared t dx squared is 0, which was our original differential equation. So that's kind of cool. We could integrate that equation by parts. You remember that from first year, maybe second year calculus. Integration by parts is a standard integral technique where you take two functions, in this case we and d squared t dx squared, and you try to separate them out and do the integrals in pieces. And the well-known solution for that is in the form of we dt dx evaluated at the boundaries of 0 and n in this case. So those are just discrete values at the boundaries, minus the integral of the derivative of we times the integral of d squared t dx squared. And that means now you've got an expression that is in the first derivative of w, and if that's piecewise, that's going to be a set of constants. The first derivative of temperature, if temperature is piecewise, that's a set of constants. And we've taken that second derivative that was a nasty form, and we've turned it into a derivative equation that has only first derivatives in it, which, if we assume a solution that's piecewise linear, or even if it's a polynomial, then the form and the behavior of those derivatives, now that we're working with dt dx, are pretty simple and in fact pretty manageable. So let's look at this in terms of an actual example of points. Here's points 1, 2, 3, 4, and 5. Each of them would have a temperature. And those temperatures are piecewise, are linear between them. There's an arbitrary function we, and defined by w1, 2, 3, etc. And if we write down the integral equation and we break up that integral into a piece from 1 to 2, a piece from 2 to 3, 3 to 4, 4 to 5, etc., the sum must still be 0, but now we've broken it into finite elements of the function. And we can integrate those elements separately, individually. Now the cool thing is that because we assumed a solution form as a polynomial, then we're going to find that each of those terms, dt dx and dw dx, in terms of the integrals, are actually just constants. And we can write that out and find that this becomes essentially multiplying of constants of integration, or constants of area, at each point along the solution set. And again, each discrete point. Now each multiplying term is going to have both w's and t's in it. And if you see, all that we'll have will be those discrete points of the W's and T's. If we break that out and we organize terms, you'll see that we can turn that into a fairly long and fairly nasty looking set of equations. However, you can break out all the W's outside, and those are arbitrary functions. So if those are arbitrary, then the only way that this solution set could be true is if what's inside the brackets for the T's is equal to 0 independently. So now we have a system of n unknowns, that is all the T's, and n equations where each one was for each of the W's, W1 through W5 in this case. And we can write that as a matrix, and each of the matrices has a specific name. The one on the left represents the boundary conditions, or the forcing function in some sense, the reaction. The big central one, A, is the stiffness matrix, and T is the thing we're solving for. If it's temperature, as in this example, that's what it is. In the strength of materials example, it would be deflections or stresses. Now that stiffness matrix will be huge. It could be 100,000 terms or bigger, depending on how big your finite element analysis model is. So that's a big deal. The key thing to take away from this is that finite difference is really taking the differential equations directly, making them discrete, and solving them directly. Finite element method, however, is a little more subtle than that. Finite difference, you've got the discrete partial differential equations that you solve. Finite elements, you are making some assumption about the form of the finished solution, and you're using an arbitrary element function to help make the solution work. So those are the finite pieces, and so it's key in making a solution efficient that the form of those finite W's is one that makes the solution efficient and matches the result. So essentially, the finite element method allows you to break the problem into pieces, finite pieces, and solve each one in the simplest possible function, simplest possible form. The key problem with finite difference is that you've got a rigid grid. Whereas finite elements, you have an arbitrary set of functions, and therefore you've got a grid or an element set that's extremely flexible, and you can use it for all sorts of weird geometries that you'll encounter in your daily work. You have to worry about boundary conditions. Boundary conditions are really important to defining the problem and giving you a correct solution. And likewise, the governing equations. Both methods rely upon choice of the proper simplified governing equation set for the physics you're trying to model. So thanks for watching, and I hope that this was helpful. I realize it was a rapid fire derivation and not a great derivation either. I encourage you, if you really are interested in the math, I've posted an ancient lecture from an MIT professor who gave a really good description of finite element analysis in horrible detail, getting into the Galerkin method, which is the foundation for it, and showing the difference between finite difference and finite element, and actually working through a problem and ultimately finding that you've done the finite element method solution. In contrast, there's a really great video that I've also posted with a long since retired professor, Gil Strang, who I took a calculus course from, I'm very proud to say. He describes the finite element method, and that's kind of cool because he was one of the mathematicians who was fundamental in actually creating it. Yeah, he taught me a graduate school course in calculus. I think I have his textbook kicking around someplace. So thanks for watching. I hope this helped, and well, see you soon.